Good morning, class. Today we're going to significantly expand our toolkit for differentiation. So far, we've become comfortable with differentiating basic polynomial functions. We'll be extending these ideas to cover a much wider variety of functions. Our main learning goals for today are to master several new differentiation rules. By the end of this lecture, you will be able to, first, differentiate powers of x where the exponent is any rational number. Second, find the derivatives of key trigonometric, exponential, and logarithmic functions. And finally, apply three major rules for more complex functions: the chain rule, the product rule, and the quotient rule. Let's begin by extending a rule we already know well. We'll start by extending the power rule. You'll recall from our previous work that the derivative of x to the power of n, where n is an integer, is n times x to the power of n minus 1. That is, for any integer n, the derivative of x to the n is n, x to the n minus 1. The great news is that this rule is more powerful than we've been giving it credit for. It doesn't just work for integers, it works for any rational number. So our key point here is that if f of x equals x to the n, where n is a rational number, that means any fraction, then the derivative f prime of x is still n times x to the power of n minus 1. The rule is exactly the same. Let's see this in action with an example. This allows us to differentiate functions involving roots. Let's find the derivative of f of x equals the cube root of x. The first step, whenever you see a root, is to rewrite it using a rational exponent. The cube root of x is the same as x to the power of 1/3. So f of x equals x to the 1/3. Now that it's in the form x to the n, we can apply our extended power rule. Our n is 1/3, so we bring the 1/3 down in front and subtract 1 from the exponent. The derivative is 1/3 times x to the power of 1/3 minus 1. 1/3 minus 1 is the same as 1/3 minus 3/3, which gives us negative 2/3. So our final derivative is 1/3 x to the power of negative 2/3. Let's try a more complex example where we first need to use our laws of exponents to simplify. Let's find dy by dx for the function y equals the quantity 3 x squared minus 4, all divided by the square root of x. We can't differentiate this directly. We need to break the fraction apart and write each term in the form a times x to the n. First, we can split the fraction into two terms: 3x squared over the square root of x minus 4 over the square root of x. Remember that the square root of x is x to the power of 1/2, so we can rewrite the expression like this. Now we use our exponent rules. For the first term, we subtract the exponents. 2 minus 1/2 is 3/2. For the second term, we bring the x to the numerator, which makes the exponent negative. So our function is y equals 3x to the 3/2 minus 4x to the negative 1/2. Now it's just a matter of differentiating term by term using the power rule. For the first term, we multiply by 3/2 and subtract 1 from the exponent. For the second term, we multiply by negative 1/2 and subtract 1 from that exponent. Let's simplify. 3 times 3/2 is 9/2. 3/2 minus 1 is 1/2. In the second term, negative 4 times negative 1/2 is positive 2. And negative 1/2 minus 1 is negative 3/2. So the final derivative is 9/2 x to the 1/2 plus 2x to the negative 3/2. So we've successfully extended the power rule to rational exponents, which is a very useful expansion of our capabilities. Alright, let's move on to a new class of functions, trigonometric functions. In this section, our goal is to learn the derivatives of sine and cosine. We'll be looking at the derivatives of sine x and cosine x. There is one extremely important condition for these rules to work. The angle, x, must be measured in radians. If you're working with degrees, you must convert to radians before differentiating. I'll repeat that because it's a common mistake. These rules only apply when x is in radians. The rules themselves are quite straightforward. Let's look at the first one. The derivative of the sine function is the cosine function. If f of x is sine x, its derivative is cosine x. And for cosine, it's very similar. The derivative of the cosine function is the negative sine function. So if f of x is cosine x, its derivative is negative sine x. Be careful with that negative sign. Just like with polynomials, these rules can be applied to multiples and sums of terms. Let's work through an example. we want to differentiate f of x equals 2 sine x minus 5 cosine x. We can differentiate this term by term. The derivative of the whole function is the derivative of the first term minus the derivative of the second term. The constants, 2 and 5, can be brought out in front. So we have 2 times the derivative of sine x minus 5 times the derivative of cosine x. Now we apply our new rules. The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Finally, we simplify. The 2 negatives in the second term make a positive. So our final answer is 2 cosine x plus 5 sine x. And now we have learned the derivatives for sine and cosine. Next up are 2 other very important functions in mathematics, the natural exponential function and the natural logarithm function. Our objective here is to learn their derivatives. We're focusing on the derivatives of e to the x and the natural log of x. Let's start with the exponential function, e to the x. This function has a truly remarkable and unique property. The derivative of e to the x is simply e to the x. The function is its own derivative. This means that at any point on the graph of y equals e to the x, the value of the function is equal to the slope of the tangent line at that point. It's a very special property. Now let's consider the natural logarithm, which is the inverse of the exponential function. The derivative of the natural log of x is 1 over x. This is another fundamental rule you'll need to memorize. You might wonder where this rule for the natural log comes from. We can actually prove it using what we know about e to the x and the geometry of inverse functions. Let's walk through that proof. We want to prove that the derivative of y equals ln of x is 1 over x. We'll start by graphing y equals e to the x, and its inverse, y equals ln of x. Remember that the graphs of inverse functions are reflections of each other across the line y equals x. Here are the graphs. The blue curve is y equals e to the x, and the green curve is y equals ln of x. They are reflections across the dashed line y equals x. Let's pick an arbitrary point P on the curve, y equals e to the x. We'll call this point P. If its x-coordinate is P, then its y-coordinate must be e to the power of Page. So the point P is P e to the P. We know the derivative of e to the x is e to the x. So the gradient of the tangent line at point P is simply e to the P. The slope of the tangent at P is e to the P. This represents the rise over run of the tangent line. Now let's consider the corresponding point Q on the graph of y equals ln of x. Since it's a reflection, we swap the x and y coordinates. The reflected point Q will have the coordinates e to the P, comma P. Here's the clever part. When you reflect a line across y equals x, the rise and run are swapped. So the new gradient is the reciprocal of the old gradient. The gradient of the tangent line at Q is 1 over the gradient at P. That means the gradient at Q is 1 over e to the P. We're almost there. We have the gradient at point Q, but it's in terms of P. We want it in terms of the x-coordinate of Q. Look at the coordinates of Q. The x-coordinate is e to the Page, so we can replace e to the P in our gradient formula with x. This tells us that the gradient of y equals ln of x at any point x is 1 over x. And that completes our proof. For y equals ln of x, the derivative of y prime is 1 over x. Let's do a quick example using this new rule. Let's find the derivative of y equals the natural log of x cubed. Now, we could use a more advanced rule we'll learn later, but for now we can simplify this using a law of logarithms first. The power rule for logarithms says we can bring the exponent down as a coefficient. So y equals ln of x cubed is the same as y equals 3 times ln of x. This is much easier to differentiate. The derivative, y prime, is just 3 times the derivative of ln of x. Since the derivative of ln of x is 1 over x, our final answer is 3 over x. This shows how knowing your log rules can simplify differentiation problems. Okay, we've just learned a handful of new, important derivative rules. A key application of derivatives is finding the equation of a tangent line to a curve. Let's see how we can use our new rules to do just that. Our objective is to apply these new rules to find the equation of a tangent line. Remember, To find the equation of any straight line, we need two things: a point on the line and the gradient of the line. We use the point slope formula, y minus y1 equals m times x minus x1. The gradient of the tangent line quos m is found by calculating the derivative of the function and evaluating it at the point of tangency. Let's work through this example. We need to find the equation of the tangent to the curve y equals cosine x plus 2 e to the x at the point 0, 3. We are given the point x comma y as 0, 3, so we just need to find the gradient, m. First, we differentiate the function y with respect to x to find the general formula for the slope of the tangent at any point. Using our new rules, the derivative of cosine x is negative sine x, and the derivative of 2e to the x is just 2e to the x. So our derivative is y prime equals negative sine x plus 2e to the x. This formula gives us the gradient for any x. We need a specific gradient at our point where x equals 0. So we substitute x equals 0 into our derivative expression. The gradient m is equal to negative sine of 0 plus 2 times e to the power of 0. Now we just need to evaluate this. Remember that sine of 0 is 0, and any number to the power of 0 is 1. So we have 0 plus 2 times 1, which gives us a gradient of 2. We have our point, 0, 3, and our gradient m equals 2. Now we can write the equation of the line. Substituting our values into the point slope formula, we get y minus 3 equals 2 times the quantity x minus 0. Simplifying this gives us our final answer. The equation of the tangent line is y equals 2x plus 3. So you can see how our new derivative rules fit directly into the methods we already know. Alright, we're now going to introduce one of the most important and powerful rules in all of calculus. This is the chain rule, and it's used for differentiating composite functions. Our objective is to understand and apply the chain rule for composite functions. What is a composite function? It's a function within a function. Think of it like Russian nesting dolls. Mathematically, we write this as f of g of x. There's an outer function, f, and an inner function, g. For example, in a function like y equals sine of x cubed, the outer function is sine, and the inner function is x cubed. Or, in y equals the quantity x squared plus 1, all to the power of 5, the outer function is, quote, to the power of 5, and the inner function is x squared plus 1. These are examples of composite functions. Our existing rules for sums and products don't tell us how to handle this, quote, function within a function structure. This is where the chain rule comes in. It gives us a method to differentiate these composite functions. Here is the rule in Leibniz notation, which is very intuitive. If y is a function of u, and u is a function of x, then the derivative of y with respect to x is the derivative of y with respect to u, multiplied by the derivative of u with respect to x. Think of it this way. To find the rate of change of the outer function with respect to x, you first find its rate of change with respect to its immediate input, uu, and then you multiply by the rate of change of that input with respect to x. You're creating a, quote, chain of derivatives. A simpler way to remember it is, you take the derivative of the outer function, leaving the inner function alone, and then you multiply by the derivative of the inner function. Let's see how this works in practice. Now that we have the formula for the chain rule, let's solidify our understanding by working through several examples. Our goal here is to become proficient in applying the chain rule. Let's start with y equals the quantity x squared minus 3x, all raised to the 6th power. The first step is to identify the outer and inner functions. We'll call the inner function ju. The outer function is something raised to the 6th power, so y equals u to the 6th. The inner function, the something being raised to the power, is u equals x squared minus 3x. Now we apply the chain rule formula. dy dx equals dy slash du asterisk du slash dx. We need to find those two derivatives. First, the derivative of y with respect to u. The derivative of u to the 6th is 6u to the 5th. Second, the derivative of u with respect to x. The derivative of x squared minus 3x is 2x minus 3. Now we multiply these two parts together. So dy by dx is equal to 6u to the fifth times the quantity 2x minus 3. The final step is to replace u with its original expression in terms of x, because our final answer should only have x in it. We replace u with x squared minus 3x. The final derivative is 6 times x squared minus 3x to the fifth, all times 2x minus 3. Let's try another one, this time with a trigonometric function. Let's differentiate y equals sine of 4x. Here, the outer function is sine of something, so y equals sine u. The inner function is u equals 4x. The derivative of sine u is cosine u. The derivative of 4x is just 4. Multiplying them gives us cosine u times 4. Substituting u back gives us our final answer, 4 times cosine of 4x. Notice the pattern. Derivative of the outside cosine with the inside untouched times the derivative of the inside 4. Let's do one more with an exponential function. Let's differentiate y equals e to the power of 3x squared. The outer function is e to the u, and the inner function is u equals 3x squared. The derivative of e to the u is just e to the u. The derivative of 3x squared is 6x. Multiplying them gives e to the u times 6x. Substituting u back, we get our final answer, 6x times e to the power of 3x squared. As you can see, the process is always the same. Identify the inner and outer functions, differentiate both, multiply, and substitute back. With practice, you'll be able to do this in one step. We've seen how to handle sums, differences, and now composite functions. But what if we need to differentiate a product of two functions? For that, we need the product rule. Our next objective is to learn the product rule. A very common mistake is to think that the derivative of a product is the product of the derivatives. This is not true. Let me repeat. The derivative of u times v is not the derivative of u times the derivative of versus. For example, the derivative of x squared is 2x. But if we think of x squared as x times x and differentiate each part, we get 1 times 1, which is 1. Clearly, 2x is not equal to 1. So we need a special rule for products. Here is the product rule. If y is a product of two functions, u and versus, then its derivative is the first function times the derivative of the second, plus the second function times the derivative of the first. Using prime notation, it's y prime equals uv prime plus vu prime. This is a fundamental rule you must memorize. Let's apply it to an example that we couldn't do before. Let's differentiate y equals x squared times the natural log of x. This is clearly a product of two functions. We'll identify them as u and v. Let's set u equal to x squared and v equal to the natural log of x. Next, we need their derivatives, u prime and v prime. The derivative of u, which is x squared, is 2x. The derivative of v, which is ln of x, is 1 over x. Now we have all four components. We just need to substitute them into the product rule formula, uv prime plus vu prime. Substituting in, we get x squared times 1 over x, plus the natural log of x times 2x. The final step is to simplify the expression. X squared times 1 over x simplifies to just x. So the final derivative is x plus 2x times the natural log of x. And that's how you apply the product rule. Things get really interesting when we have to combine our new rules. Let's tackle a problem where we need to use both the product rule and the chain rule. Our objective is to see how these rules can work together. We're going to combine the product rule and the chain rule. Consider the function f of x equals e to the x times the quantity x squared plus 3, all to the power of 4. When you look at this function, the outermost structure is a product. It's one function, e to the x, multiplied by another function, x squared plus 3 to the fourth. So we start with the product rule. We'll define our two functions for the product rule. Let u equal e to the x, and let v equal x squared plus 3 to the fourth. Now, we need to find the derivatives of u and versus. The derivative of u is straightforward. The derivative of e to the x is just e to the x, so u prime is e to the x. Now for v prime. Notice that v itself is a composite function. To differentiate v, we must use the chain rule. To find v prime, we need the chain rule. The outer function is quo to the power of 4, and the inner function is x squared plus 3. Applying the chain rule, we get the derivative of the outside, which is 4 times the inside to the power of 3, multiplied by the derivative of the inside, which is 2x. Simplifying, v prime is 8x times x squared plus 3 cubed. Okay, now we have all 4 pieces, u, v, u prime, and v prime. We can plug them back into the product rule formula. The product rule is u v prime plus v u prime. Substituting our parts, we get e to the x times our expression for v prime plus our expression 4 versus times e to the x. This is the derivative, but we should always try to simplify it. We can factor out common terms. Both terms have a factor of e to the x and a factor of x squared plus 3 cubed. Let's pull those out. From the first term, we're left with 8x. From the second term, we're left with one factor of x squared plus 3. Cleaning up the last part gives us our final, simplified answer. This example shows how you must first identify the main structure of the function, in this case, a product, and then apply other rules as needed for the individual parts. We've handled products, so the natural next question is, how do we handle quotients, or functions that are fractions? For this, we have the quotient rule. Our objective now is to learn and apply the quotient rule. Just like with products, you cannot simply differentiate the numerator and denominator separately. There is a specific formula we must use. Here is the quotient rule. If y equals u over v, the derivative is the bottom function times the derivative of the top, minus the top function times the derivative of the bottom, all divided by the bottom function squared. There's a popular mnemonic to help remember this. Low d high minus high d low over the square of what's below. Low is the denominator, high is the numerator, and d means derivative. Let's say it again. Low d high minus high d low over the square of what's below. The order of subtraction in the numerator is critical, so this mnemonic is very helpful. Let's apply this to a fairly complex rational function. We'll differentiate y equals x squared plus 6, x minus 2, divided by x plus 3 squared. First, identify the high and low functions, u and v. Our numerator, u, is x squared plus 6x minus 2. Our denominator, v, is x plus 3 squared. Next, we need their derivatives, du dx and dv slash dx. The derivative of u is straightforward, 2x plus 6. For the derivative of v, we need the chain rule. The derivative is 2 times x plus 3 to the power of 1 times the derivative of the inside, which is just 1. So dv slash dx is 2 times x plus 3. Now we have all 4 parts. We substitute them carefully into the quotient rule formula. This looks complicated, but we just need to be systematic. It's v times du dx minus u times dv zx all over v squared. Now begins the algebraic simplification. Notice that there is a common factor of x plus 3 in the numerator. We can cancel one factor of x plus 3 from each term in the numerator with one from the denominator, which now becomes x plus 3 cubed. Now we expand the numerator and collect like terms. We multiply out the brackets. Be very careful with the negative sign on the second bracket. It changes the sign of every term inside. Finally, we see that most of the terms in the numerator cancel out. The 2x squared terms cancel, the 12x terms cancel, and we're left with 18 plus 4, which is 22. Wait, let me recheck the calculation from the book. The book has a different expansion. Let's recheck. X plus 3, 2x plus 6 is 2x squared plus 12x plus 18. And 2x squared plus 6x2 is 2x squared plus 12 by minus 4. So the numerator is 2x squared plus 12x plus 18 minus 2x squared plus 12x4 equals 18 dash minus 4 equals 22. The book has minus 22. Let me check the book's substitution step. I see the book has the terms in a different order in the numerator. Let's follow the book substitution exactly. It seems to have u v dzis, v zis u. Let's reevaluate. The formula is v asterisk u vz minus u minus v. So x plus 3 squared asterisk 2x plus 6 minus x squared plus 6 x2 asterisk 2x plus 3. The book substitution is correct. Let's recheck the expansion. X plus 3, 2x plus 6 equals 2x squared plus 12x plus 18. And 2x squared plus 6x2 equals 2x squared plus 12 by minus 4. So the numerator is 2x squared plus 12x plus 18 minus 2x squared plus 12x4 equals 22. It seems there might be a typo in the textbook's final answer. Based on our calculation, the numerator should be positive 22. Let's proceed with our result. The derivative is 22 over x plus 3 cubed. To cap off our lesson on these new rules, let's use the quotient rule to derive the formula for the derivative of another important trigonometric function, the tangent function. Our objective is to find the derivative of f of x equals tangent x. We don't have a basic rule for tangent, but we can express tangent in terms of sine and cosine, which we do know how to differentiate. We know that tangent x is equal to sine x, divided by cosine x. This is a quotient, so we can use the quotient rule. Let's set up our quotient rule problem. The numerator, u, is sine x. The denominator, v, is cosine x. Now we find their derivatives. The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Now we substitute these four pieces into the quotient rule formula, vu prime minus uv prime, over v squared. Substituting gives us cosine x times cosine x minus sine x times negative sine x, all divided by cosine x squared. Let's simplify the numerator. Cosine times cosine is cosine squared. The two negatives in the second term make a positive, giving us plus sine squared x. So the numerator is cosine squared x plus sine squared x. This numerator should look very familiar. It's the fundamental Pythagorean identity in trigonometry. We know that cosine squared x plus sine squared x is always equal to 1. So our derivative simplifies to 1 over cosine squared x. This is a perfectly correct answer, but it's often written in another form. Remember that 1 over cosine x is the secant function, sec of x. Therefore, 1 over cosine squared x is secant squared x. This is another key derivative to memorize. The derivative of tangent x is secant squared x. Alright, that brings us to the end of our lecture. Let's take a moment to summarize the powerful new differentiation rules we've covered today. We've added a lot to our calculus toolbox. First, we extended the power rule to all rational exponents. The derivative of x to the n is n times x to the n minus 1, now for any rational number n. Then, we learned the derivatives of four fundamental functions. The derivative of sine is cosine, of cosine is negative sine, of e to the x is e to the x, and of natural log of x is 1 over x. Finally, we introduced the three major rules for handling more complex combinations of functions. The chain rule for composite functions, the product rule for products of functions, and the quotient rule for divisions of functions. These rules, especially when used in combination, dramatically increase the range of functions we can analyze. Mastering them is crucial for your continued success in calculus. Make sure to get plenty of practice with the exercises. That's all for today. Thank you.